So welcome to Lab 1 for Physics 2. This is the charge tape experiment. So the purpose of this lab was to observe the interactions between charge tape and other materials, and then to determine the amount of excess charge present on the charge tape based off those interactions. So this lab had both a physical section and then also a computational model section. So the materials were clear tape, ruler, flat surface, structural support objects, and pen, and then also something to measure the mass of the initial tape. And then also we used GlowScript for that computational model. And right off the bat, the results, the charge on the tape was positive. So we see it was 1.32 times 10 to the negative 8th coulombs. And the number of calculated electrons lost by the charge tape was then 8.25 times 10 to the 10th electrons. So fundamental principles that are necessary for this experiment are Newton's second law. So the system's change in momentum is proportional to the net force applied. We see this whenever things are starting to move. We can kind of see those principles pull in. So that's F is equal to ma. And then for Coulomb's law, this plays a huge part in this experiment. And this describes the force of attraction or repulsion between two charged objects. So in this experiment, we see a lot of interaction between positively and negatively charged particles. And then for the gravitational force, this describes the attractive force between two objects with mass. This also plays a role since we are hanging the tape on stuff in this experiment, so gravitational force is something we have to think about. And then also conservation of electrical charge plays a huge part in this experiment. So electric charge cannot be created or destroyed, only transferred. And in this experiment, it's important to note that all of the electric charge is just being transferred from object to object, as opposed to creating new charge altogether. So some initial conditions and numbers. You can also see some of the startup of the experiment in those pictures there. The tape mass was measured to be 4 times 10 to the negative 4th kilograms. Tape length is 0.2 meters. So I did use packing tape for this as opposed to scratch tape because that's what I had in my house. So the tape width is a little bit thicker. It's 0.05 meters. And then the tape area is 0.01 square meters. Obviously just the width times the length of that tape. The atom area is there. I also have some calculations shown at the end of the slides that I can show how I got that. And then the number of atoms is also there. So 1 times 10 to the 18th atoms. So for the model, the system was tape B, and then the surroundings was tape A, and then the distance between the two tapes at which lifting started to occur was 0.02 meters. So now calculating the excess electrons, I have some of my work here. So you can see I calculated first the force of gravity, just using that mg equation. I also noted the distance of float. I then calculated the charge on tape B, and I used d, the distance of the float, to determine q, or the charge in that on the particle, which was 1.32 times 10 to the negative 8th coulombs. I then determined the number of electrons that were on tape B. Since we know the number of atoms, we know the charge, we know all of these things, this is something that was very easy to come up with, and we can see the number of electrons that were transferred. So because there's a positive charge, that means that the charge tape had a deficit of electrons, or it lost electrons. And then you can also see I calculated the atoms, and then the ratio of electrons per atoms in the 7.2.1. So for the computational model at point charge, I'm also going to attach my exact flow script to the bottom of this YouTube link. So be sure to check that out if you want more details. But this was for the point charge model, and you can see that we have that like upward electrical force and then the downward gravitational force, and they should be equal magnitude since we aren't seeing any acceleration. This is the other computational model for the one we were given. I'm not exactly sure why the electrical force has such a small magnitude in this. It should not. It should, again, be equal to the force of gravity. So not sure what's going on there. But again, I'm going to attach my GlowScript code, and you can see most of it here and kind of see what I did. So some assumptions is that both U-tapes have the same net charge, and the tapes can be treated as a single point charge for the calculations. Some shortcomings of this is that there may be minor differences in the net charge between the tapes, and also charge is, of course, not localized to a single point on the tape, but is rather spread out across the area. So the point charge model doesn't really represent what we're actually seeing in real life. So for discussion, I did do my hypothesis. I said if the two charge tapes were brought close to each other, they would lean away from each other. This wasn't exactly correct, just because we were holding tape A in place, so only tape B was able to move. And then for 6.2, I have some additional discussion. So I said, U-tape's positively charged, it should lead towards a negatively charged pen. This was demonstrated and tested. This is what happened. And then also if it's neutral, the tape would also lean towards the pen. So in 7.1, I did some additional discussion points, and you can see my force diagram there. And then also I talked about momentum and also the electrochemical force on it and the distance. So feel free to pause the video and read through that.